Hello, everybody. So I just finished up my undergraduate degree, and for my senior thesis, I was taking a look at covers of abstract tropical curves. And because we've only got 5 minutes here, I'll just give you a high-level overview of some of the things I was looking at. So first, I want to define what an abstract tropical curve is, as opposed to the more concrete tropical curves that we saw in one of the talks yesterday, where they're living in the plane. So here, I'll define an abstract tropical curve to be a metric graph. So let me do this. It is a metric graph. So just a graph with lengths on its edges. And we need 2 conditions to be satisfied. Technically more, but for brevity, I'm just going to talk about the 2 more important ones. So each vertex either is one valent, meaning it only has one edge, or has a valence of at least 3. So we don't want any 2-valent vertices in our graph. A very simple example of one of these abstract tropical curves is this guy here, the tripod. This is perhaps the simplest non-empty graph. Now, I'll also give a condition on our edges, on the metric, on the length of our edges. So edges, if an edge E is adjacent to a 1-valent vertex, then the length of the edge we'll just say is infinite. So in this case here, all 3 of those edges are adjacent to a 1-valent vertex, so they all have length infinity. Now, because I don't have enough chalk, I didn't draw those to scale, but they've got an infinite length. Otherwise, if E is not adjacent to a 1-valent vertex, it'll have some real length. So the length of E will be some real number. There are no of those edges in this graph here. We'll call those edges inner or bounded edges, and these edges here ends. So now we can actually look at our covers. So that's just a abstract tropical curve, but we want a cover of an abstract tropical curve. So a cover of one of these guys is another metric graph and a continuous function between them. So let's give an example here. Okay. So if we take this graph here and we just project down, so this point would map down here, both of these points would map down here, for instance. This is a continuous function, and we want it to be the case that if we restrict this function to one of the edges in our upstairs graph here, that this is some affine linear function on the coordinate. If we give a coordinate to one of these edges, this function is affine linear, and we'll call the slope here the weight, and the weight will be an integer. So an example of a cover is this, what I've got drawn right here, and I want to put some weights on this. So the weights that we have as our slopes to this function, I'll just use these numbers 1, 1, 2, and 2, and there's a specific reason. We can't just choose any numbers. We need the weights and the graph itself to satisfy a sort of combinatorial version of the Riemann-Hurwitz formula, which for sake of time I'm not going to write out, but I'm happy to do so if you're interested. And what I was looking at in my thesis was taking a look at these guys and then looking at them under the action of a group. So there's in some sense a way to make these covers compatible with a group action. I specifically looked at the Klein 4 group, but you can do this with other groups as well. With the remainder of my time, I just want to give a more complicated example of a cover than that one there. So let's see if I can draw this quickly. Just something, because they don't have to be as simple as what I just drew. So all of these are 2s. and then a bunch of 1s here. So this is our covering graph. And it goes down to a much simpler graph. This, right? So pretend this is in line with these vertices here. So this is a degree 4 map, right? Because each preimage, if we add up the weights of the preimages, we get 4. And these numbers, the reason we want them to be integers, there's a certain way that they correspond to the ramification indices of a cover of the Riemann sphere. And that's actually one way we can construct these covers, is by looking at a ramified cover of the Riemann sphere. Thank you.